Hello and welcome back. So today I am very happy to introduce a new subject that we're going to be covering, and we're going to be discussing discrete math for the next handful of videos. So hopefully we'll have a nice series by the end of this on discrete math related topics. Um, so the first one that we're going to discuss today is sets. So we're going to do an introduction to sets, learn some of the definitions related to sets, and conduct some proofs related to sets. So in many discrete math courses, having this strong foundation of sets is incredibly important. So that's what we're going to cover today. So let's jump into it. So we'll start with definitions. There are a lot of set definitions, but I think many of these are quite intuitive, but it's still important that you take the time to fully understand everything and make sure you're comfortable with these words and this vocabulary so you can use them all the time. So, first of all, what is a set? Simply, it's just an unordered collection of distinct objects. So the keywords here are unordered and distinct. So, the set of English vowels is A, E, I, O, U. Notice how they're all different from each other. Now, this set is the same set as O, A, I, E, U. The only difference between these two sets is the arrangements of the letters, the arrangement of the letters. But you can see that, okay, there's an A here and one here. E is in both of these sets. I also in both of these sets, same with O and U. So they contain the same elements, they're just in a different order, but that makes those sets the same. Also note how there's no repetition of letters. So we don't have A, E, I, O, U. That wouldn't be a set. They have to be distinct objects. And so we move to the second bullet point, which I kind of touched upon. Set A is equal to set B if both of those sets contain the exact same elements. So in this case, these two sets are equal because they both contain the exact same elements. They're just arranged differently. Next, we'll move on to cardinality. So the cardinality of a set, which we'll call the set S, it's denoted as S with these bars around it. That's simply the number of elements in S. So if we go back to our set of vowels, the cardinality of that set is 5 because there are 5 vowels. We can count them A, E, I, O, U. That gives 5. So that's cardinality. Cool. So the next one is super important, subset. We'll see this a lot. So it's important to understand this. So a set S is a subset of another set, which we'll call B, if and only if every single element of S is also an element of set B. Okay, so our notation for this is S, and then this little symbol here, B. So the way I like to think about it is, say we have like this circle, and we call this B, and there could be some elements in here. Let's say they're numbers 3, 4, 5, right? Let's say that's our set B. So S is a subset if we can draw this circle here. If this is S, then S is a subset of B because all of those elements contained within S are also contained within B. So that's one possibility for S. Similarly, that's another possibility for S where it just contains one element. Here are some interesting cases. In this case, S is also a subset of B. Even though S doesn't contain anything, it's still a subset of B. In this case, S is the empty set. We'll touch on that in just a moment. But notice how it's still contained within B. And then another important one to think about is this one, where S contains the numbers 1 through 6 in this case, and all of those are included within B. So we know that in this case, S and B are equal, but here we would still say that S is a subset of B. So that's how I like to imagine it with these circles and one circle contained within another circle. Let's give a non-example. So let's say uh, outside of B, there's some other numbers like 7, 8, 9. Then in this case, S would not be a subset of B because there's some elements in S which are not contained within B. So we can see how S's circle, well, I guess it's not a circle, but S's region is not fully contained within B. Okay, so let's move to the last bullet point. The empty set, which I briefly discussed, and we denote that with the Greek letter phi or phi, um, that's a set that contains no elements. So the cardinality of phi is equal to 0, right? That should make sense. It doesn't have any elements, so its cardinality is 0. And phi is a subset of S for all sets S. Okay, so those are some introductory properties, but there's still a lot more to cover. Let's move onwards. So for any set S, doesn't matter what the set is, we have the following two properties. The empty set is a subset of S, and S is a subset of S. So think about my circle diagram here, where S was just this little region here which didn't contain anything. That was the empty set example. And then when S contained all of these elements, that was the full example where S is a subset of S, or in that case, S was a subset of B. But these are two properties to remember. Key thing here is any set. So if S equals, say, the empty set, it's still a set, so we can still have that the empty set is a subset of the empty set, and, well, I guess this property here would tell us the same thing. But yeah, that's another thing to notice, that the empty set is a subset of the empty set. Pretty interesting. Okay, so now for some reason, there's a symbol that looks very similar to subset, but it's just slightly different. Don't ask me why it's the case. But that is this right here. So when A, and if we have sets A and S, and A is a subset of S, and A does not equal S, then A is called a proper subset of S, and that's when we use this notation. So the only difference between the notation is the lack of the bar underneath it, and the only difference is that A does not equal S in this case. So yeah, when we use this, A subset of S, this does not mean that A has to equal S. It's just not as strict of a symbol as this one is. So that's the difference. And here we have A is a proper subset of S if and only if, first, it has to be a subset of S, and second, there exists some element Z in S such that Z is not in A. And this is just saying that those sets S and A are not equal. Because what does it mean for two sets to not be equal to each other? Well, that means there's got to be one element in some set that's not in the other. So that's this thing right here. Okay, so next we have the power set. So the power set of a set S is denoted as P of S, and this is the set of all possible subsets of S. It's kind of confusing, a lot of sets here, and it takes a moment to think about it. But the key thing to notice is that the power set is a set. And I know it says set in the name, but sometimes we forget about this. But yes, the power set is a set, and the elements of P of S are all of the subsets of S. So if we were to take any element from P of S, that should be a subset of S. So let's take a look at this example here. We have S is equal to 1, 2, and 4. We know that's a subset. Why do we know, or we know that's a set. And why do we know that? Well, because all of these elements are distinct from each other. Okay, so then the power set of S should contain all of its subsets. So a subset, if we recall, is like a smaller version of the set. Basically, every element within our subset has to be included within S. So here we've enumerated all of the subsets. So first remember the empty set is a subset of S. Then we have the set containing only the element 1 because this is contained in S. Then the element containing 2 and the set containing 2 and the set containing 4. Those all work. Then we move on to 2 element subsets. So 1, 2, 1, 4, 2, 4. And then finally 3 element subsets 1, 2, 4. Couple thing to notice. First, we don't have any elements in P of S that contain more than 3 elements because our set S has cardinality 3. So if we had an element of P of S with say 4 or 5 elements, then that wouldn't be a subset of S, and that would violate the definition of power set. Second thing to notice is if we look at how many elements are in P of S, we get 1, 2, 3, 4, 5, 6, 7, 8. So in this case, we have the magnitude of the power set of S is equal to 8, and that happens to be 2 cubed, and 3 happen to be the magnitude of S. So in this case, it seems that the magnitude of the power set is 2 to the power of the cardinality of that set. Now it takes a moment to think, like, is this just a coincidence or is this actually factual? Well, why don't we explore that? Let's think about how we create subsets. A simple process is we just go through every element of our set and we say yes or no. And that just depends on whether or not you want to include that element in your subset. So if we have this set here, 3, 2, 4, 5, and we point to the first element, 3, and we say yes, that means we're going to include 3 in our subset. Then we point to the second one. Let's say yes again. So we include 2 as well. We point to the third element, which is 4. Let's say we say no. So we don't include 4. And then we point to 5. We say yes. So we include that. So we said yes 3 times to 3, 2, and 5. So we get this set here, 3, 2, and 5. And this indeed is a subset of that, right? So it's a simple process for just saying yes or no to each element. So there's like 2 options for each element. Like either we say yes or no of whether or not we want to include it in our subset. And so if there's 2 options for the first one and 2 options for the second and 2 options for the third and 2 for the fourth, we just multiply 2 that many times and we get 2 to the power of the cardinality of S as the number of subsets. So the reason why we multiply is due to the independence of the selections, but you can try to prove it to yourself why it's not adding or some other operation between those twos. And a good way of doing that is writing out all of the subsets and seeing why that's different. But yeah, so it does seem to be factual that this property holds. So this is something to be aware of and perhaps something to memorize. Great. Now let's discuss some set operations. So we've discussed a lot of definitions. These are some more definitions, but they relate to how we can operate on sets and create new sets. So for the examples, we'll let A be this set, 1, 3, 5, and B is 2, 3, 4. So first is the union of the 2 sets, and that's denoted as A, and then this like U symbol, B, I just call that union, I think most people do. So A union B, and that is the set that contains all elements in either A or in B. So A union B is a set, and in this case, the union of A and B is 1, 2, 3, 4, 5. And the way we check that is, well, we can go through all of the elements in A and B, and we want to make sure that that element is included in A union B. So 1, yes, that's included in A union B. 3, yes, that's included. 5, yes. 2, yes. 3, yes. 4, yes. Wonderful. Now, a subtle thing to notice is that the number 3 appeared in both sets A and B, right? And that's fine because they're different sets. But notice how it only appears once in A union B. The reason for that is A union B is a set, so it has to have distinct elements. So we only need one copy of the 3. Next is the intersection, and that's denoted as A, and then this like upside down U thingy, which we just say intersect. So A intersects B, and that is also a set, but that's the set that contains elements in both A and B. So the way we can do this is just look at both of our sets and determine which elements are in common to both. So we can actually just look at one set and then check the other set for it. So the first element, is 1 contained in B? No, so it's not included in our intersection. Is 3 included in B? Yeah, it's right here. So it's in both A and B, so we include it in our intersection. Next, 5, is that included in B? No, so that's it. Our intersection of A and B, in this case, it's just the set that contains 3. Finally, we say that two sets are disjoint if their intersection is empty. So that means the two sets share no elements in common. So in our example up here, A and B, these are not disjoint because their intersection is not empty. It contains the element 3 here. So they're not disjoint. But let's say we introduce the set C, which is 2, 4, and 6. Then A and C, I should probably scroll down a bit. A and C are disjoint because their intersection is empty. We can just do the same thing, compute the intersection. Let's write it out. A intersect C is going to be equal to, well, let's go through it systematically. Is 1 contained in C? No, so we don't include it. Is 3 contained within C? No, so we don't include that. Is 5 contained in C? Also no, so we don't include that. We have exhausted all elements of A, so the intersection of A and C is the empty set, 5. So in that case, those sets are disjoint. So disjoint is a very common word, we'll be using it a lot, so it's helpful to know. All right, a couple more set operations. So we'll use the same sets as before, 1, 3, 5, 2, 3, 4. I've color-coded it just for the last example, but first let's look at the difference. So the difference of A and B, which is A slash B, this can be called minus or set minus. Those are the common terms for it. So that is going to be a set, important to note, and that contains the elements in A, but not in B. So notice the ordering of A and B, and we'll see that right here. So A set minus B should be elements in A and not in B. So the way I like to compute this is go one by one through the elements in A, whatever comes first, and then check if it's included in B. If so, then we're going to remove it. If it's not included in B, then we keep it. So first we look at 1. Is that included in B? No, so we're going to keep that in our set. 3, is that included in B? Yes. It's right here in the middle, so we're not going to include that in our set. 5, is that included in B? No, so we do keep that. So A set minus B is 1, 5. Now notice that B set minus A is different than A set minus B. So we can do the same procedure where we look at the first set, the thing that comes first, and go through, see if it's included in the other set. So is 2 included in A? No, so we keep that. Is 3 included within A? Yeah, it's right there, so we don't include that. Is 4 a part of A? No, so we keep that, we get 2 comma 4. So the important thing to notice is how those two are not necessarily equal to each other. It's a good exercise to think, when does A set minus B equal B set minus A? Just something fun to think about. Next, we have the complement of a set A, and that is the set of elements not in A. And that really depends on the universe. So we can discuss this for quite a bit, but I won't spend too much time on it. Let's just say A is the set of all even numbers, or even positive integers. And our universe is just all positive integers, right? So A would be a subset of U in that case. So then A complement is denoted with a bar over the A. That would be all elements in the universe, so all positive integers that are not a part of A. So all positive integers that are not even, so that would be all odd positive integers. So the main thing to take away here is what it means is that like the elements not in A are included within the complement, and that's the symbol we use. We just put a bar over the set. Finally, we have the Cartesian product or the cross product of two sets, and that's denoted with this little cross in the middle. So that's not times, at least with sets, we call it cross, so A cross B. That's the set, again, it's a set, of all ordered pairs. And these pairs are formed by taking an element of A with an element of B in all possible ways. So in terms of set notation, A cross B is the set of all pairs A comma B. This bar means given, so all A comma B, or such that A, which is the first element of the pair, that comes from capital A. So capital A is the set. So this little a is an element of A, and little b is an element of B. So this first element should come from this set, and this second element should come from this set. So if we look at our example here, remember A is 1, 3, 5, B is 2, 3, 4. This is what A cross B is equal to. See, we have a 1, comma 2. So 1 comes from A, that's right up here, and this 2 comes from here. 3, comma 2, same thing. We take an element of A and match it with an element of B, and we do that in all possible ways. And notice how A cross B is itself a set, so we don't have duplicate items. Now note that if we were to do B cross A, that would be different. Here we would be pairing, the first element of the pair should come from B, and the second element of the pair should come from A. So I'll start to enumerate some of these. It'll be 2, comma 1, 2, comma 3, 2, comma 5, 3, comma 1, and so on. And you can start to see that it's just the mirror of the above element. And again, we can color code it. So this first element would come from B, and the second element would come from A. I forgot one, but whatever. So yeah, notice how A cross B and B cross A are not necessarily the same thing. All right, I think we've gone through all of the definitions, so we're going to move on to some problems. So this is the first problem. We have two sets, A and B, and we're going to prove that A is a subset of B. So, before we even attack this, what is our goal? To show that A is a subset of B, we want to show, WTS, that every element of A is an element of B, right? So that seems like a pretty daunting task, especially because we don't really know where A ends. Kind of goes infinitely. And it seems kind of annoying to go one by one and check whether or not that's in B, because we'd be here forever, and no one wants to waste that time. So, what we'll notice is how these sets are constructed. We'll take note of some patterns. So, if, uh, let's just say, let X be an element of A, and let it be arbitrary. So we're just letting X be some arbitrary element of A. Well, we can see that the elements of A are forming a pattern, 4 to the 1, 4 to the 2, 4 to the 3. So that means X is equal to 4 to the K for some K greater than or equal to 1. Right? I mean, that should make sense. It's just following a pattern, and the smallest K can be is 1. All right, let's take a look at B and see what we can say. So let Y be an element of B, and let it also be arbitrary. Well, let's look at what the elements of B are. 2, 4, 6, 8. Those are the even numbers, right? So Y should be even, and we can say that Y would then be equal to 2 times L for some L greater than or equal to 1. Okay, great. So now we're starting to get somewhere. We can start thinking about just an arbitrary element of A. If we can show that an arbitrary element of A is also in B, then we're good, because it's just arbitrary. So we'll start with something in this form, 4 to the K, and then show that this is an element of B. So we'll just go back, let X be an element of A, let it be arbitrary. So X is equal to 4 to the K. And we want to get it in this form, 2 times L. So we can break this down a little bit and say that this is equal to 4 times 4 to the K minus 1. And then this breaks down a little bit more into 2 times 2 times 4 to the K minus 1. And then if we just put some parentheses here, we can see that we're almost there, right? We have 2 times some quantity here, and we want it to be 2 times some quantity L, but we just need to ensure that this L is greater than or equal to 1. So if we show that this quantity in the parentheses is greater than or equal to 1, then we're good. So it remains to show that 2 times 4 to the K minus 1 is greater than or equal to 1. Well, we know that the smallest value of K is 1, right? That's what we bounded K to be. So let's consider what happens when we put K equals 1 into this. So 2 times 4 to the 1 minus 1 is equal to 2 times 4 to the 0, 2 times 1, that's equal to 2, and that indeed is greater than or equal to 1. Okay, so that's a good sign. K can only be larger than 1 or equal to it, and that would just make this quantity larger. So no matter what K is, this quantity is always greater than 1. So we can say let M equal 2 times 4 to the K minus 1. Then we have X is equal to 2 times that quantity, which is equal to M. And M is greater than or equal to 1, which we just showed up here. So that means that X is an element of B, because that was the requirement for something to be in B. It had to be of this form, 2 times L, where L is greater than or equal to 1. We've shown that here. We just use a different variable, so we're good. That's our first set-related proof. Cool. Let's move on to the next one. So let A and B be sets, just any sets. We don't know anything about them. And we're going to prove that A equals B if and only if A is a subset of B and B is a subset of A. So we'll write this in a shorthanded way. So we're trying to prove that A equals B, and then we use this double arrow to indicate if and only if. A is a subset of B, and B is a subset of A. So when we have this double arrow, we have to do two proofs, one in the forward direction and one in the backwards direction. So I'll explain what I mean. So first is the forward direction. So that means we want to prove that A equals B implies that A is a subset of B and B is a subset of A. And then secondarily, we'll prove that in the backwards direction. So that would mean that we want to prove that A is a subset of B and B is a subset of A implies that A equals B. So it's just two things, just sort of flip-flopped, but both are necessary for this proof. Okay, so let's start with the top one. We start with the fact that A equals B. Cool. So it doesn't really tell us too much. We can't really go off of that. So we have to think of some of the properties we learned about sets and subsets. So some of the things that I remember are that the empty set is a subset of S, and S is a subset of S for all sets S. So it doesn't really, it doesn't seem like we need the empty set at all. I mean, the problem just doesn't really talk about it, so I'd avoid using this. But this S is a subset of S might be helpful. Let's try using it. So we can say that A is a subset of A, and B is a subset of B. Right? That makes sense. We're just using the definition, so we can just say by definition. And if A equals B, if they're the same sets, then we can just substitute a B in for A and an A in for B. So why don't we take this B and put it right here where we see that A? So that would tell us that A is a subset of B, and why don't we take this A and put it where we see this B, and that would tell us that B is a subset of A. So we made these changes just by the fact that these two sets are equal. And so we've proven it, right? Because that's what we wanted to show here. So that was pretty easy. Now we have this second direction to prove. We start with the fact that A is a subset of B and B is a subset of A. So let's start with A is a subset of B. Similar to the previous problem, when we had these subsets, we like to think of an arbitrary element in one of the sets. So let X be an element of A and let it be arbitrary. Then, since A is a subset of B, what can we say about the membership of X and B? Well, by definition, every element of A must also be included in B since it's a subset. So, X is also in B. Cool. That's progress. But now we have this other thing to take care of. B is a subset of A. So let Y be an element of B and let that also be arbitrary. And we'll use the same logic. Then, since B is a subset of A, every element of B must also be contained within A. So Y is an element of A. And we've basically proven it, right? Just take a moment to think about what we've shown. We've shown that every element of X, or of A, we just took an arbitrary element of A, so every element of A is also an element of B. That's what the first line shows. And then the second line tells us that every element of B is also an element of A. The only way that can happen is if the two sets are equal to each other. And think back to the circle drawings, right? If this is one of our sets, and then, there's just like some I shouldn't be doing scribbles. Let me do actual numbers, right? And then we take a look at this. Those sets are not equal to each other. Let me use a different color. But we have that green is a subset of blue, but blue is not a subset of green, right? So that makes sense. That matches what we said. But if green did contain all of these elements, then the sets would be equal, and we would have this property where there are subsets in both directions. So that's the visual accompaniment for it. So that's our second proof. The main things to note here is that when we see an if and only if, it's a bidirectional thing, so we have to prove both directions. And the way we do that is we start with the first, show that it implies the second, and then we start with the second and show that it implies the first. And then just use the definitions that you know, right? We knew these two just by definition, so start out with them. If it seems like you're not given enough, just use the definitions. And then another important thing we learned is that when we do subsets, it's nice to take an arbitrary element of one set, typically the set on the left side, and see what we can say about its membership in the other set. All right, let's move onwards. So we have some sets A and B defined with some math, and we're going to show that A is not a subset of B. So, goal. To show that A is not a subset of B, it suffices, well, first of all, what does that mean? That means that every element of A, well, rather, there exists some element in A that is not in B. Because if that did not hold, then every element in A would be in B, so they would be a subset. So to show that A is not a subset of B, we must show there exists, that's the symbol for exists, some element X in A such that X is not in B. That's what we want to show. And well, we can simply do this just by giving that value, right? If we find a value in A that's not in B, then we're done. So why don't we start figuring out some values in A? So let's take a look at what A is. A is the set of n which come from the natural numbers such that n is equal to 2k squared minus 3 for some k in the natural numbers. So let's start with k equal 0. That tells us that n is equal to 2 times 0 squared minus 3. That's equal to negative 3. But negative 3 is not in the natural numbers. So negative 3 is not in A. So let's try k equals 1. So that would be n equals 2 times 1 squared minus 3. That's equal to 2 minus 3. That equals negative 1. But negative 1 is also not in the natural numbers. All right, let's try k equal 2. N equals 2 times 2 squared minus 3. That's equal to what? 4, 8 minus 3 equals 5. Okay, and 5 is in the natural numbers, so that's good. So A is going to equal to 5, and then let's do another one, k equals 3, n equals 2 times 3 squared minus 3, that's equal to 18 minus 3 equals 15, so we add 15 to the set, and that goes onwards. Let's see if any of these two elements are not in B. Well, what does B look like? B is the set of n in the natural numbers, such that n is equal to j squared plus 3 for some j in the natural numbers. All right, so let's start enumerating some of the values of B. Let's start with j equals 0. That would tell us n equals 0 squared plus 3, which is equal to 3, and that's in the natural numbers. So B, well, the number 3 will be included in B. Great, let's do j equals 1. n equals 1 squared plus 3. That's equal to 4, which is also in the natural numbers. So we include that in b. J equals 2. That would give us 2 squared plus 3, 7 in the natural numbers. And then we can continue onwards and notice that as j increases, the value of n increases, right? But already we can see we found an element a in a, which is the value of 5, which is not included in b. So we can conclude a is not a subset of b because 5 is in a, but 5 is not in b. And we're done, right? We're just providing an example, but with that example, we have proven the claim that a is not a subset of b because we found an element which is not in b but is in a. So we're done. So it's a pretty fun proof, right? And just kind of guess and you check your way through it. But the important thing to notice is that how these values kept on increasing as we increased k and j, right? If those values didn't always increase, say we went 3, 4, then -1, then we may not be able to make that conclusion because we don't know if this 5 will appear later down on the road. But we know that when we do j equals 3, that number will be greater than 7. So we'll never go back downwards. So we know we've missed a 5, so that's the counterexample. Cool. Couple more. Do we want to do this one? Yeah, okay, fine, let's do it. So once again, we have some sets given to us, and we want to prove that A is a proper subset of B. So, again, what's our goal? To show A is a proper subset of B, we must show that A is a subset of B and A does not equal B, right? Just by our definitions. Okay, so to show subset, we can just start by taking an arbitrary element of A. Let X be an arbitrary element of A. So X is equal to 4j minus 3 for some j in the natural numbers. And we want to show that this can be written as 2k plus 1. All right, well, how are we going to do this? Let's see, we can rewrite this as 2 times 2j minus 1 minus 1. Right? That's just sort of factoring out a 2, and then just subtracting 1 again, because this would give us 4j minus 2, and then we subtract 1. So we're almost there. We're kind of close, but we want it to be 2 times something plus 1. So in order for it to be plus 1, let's think about how we can alter this a little bit. So we want this to be equal to 2 times something plus 1. And this should be equal to 4j minus 3. So if we're adding 1 to get 4j minus 3, then this 2 times something should be equal to 4j minus 4. So this inside should be 2j minus 2. Okay. So we've gotten it into this form, 2 times 2j minus 2 plus 1, that's equal to 4j minus 3. So we're kind of in this form. Now we need to show that this 2j minus 2 is in the natural numbers, right? Because this k has to come from the natural numbers. So in order to compute that, we have to figure out what's the smallest that j could be, right? So what is the smallest j? Well, let's take a look from up here. We have n is equal to 4j minus 3, and we have that n is greater than or equal to 2. So the smallest j occurs when 4j minus 3 is equal to 2. And we can solve for j. 4j equals 5. J equals 5 over 4. So when j equals 5 over 4, we have n equals 2. But notice that j can't be 5 over 4 because it has to be a natural number. But the thing is that no matter what, this will be in the natural numbers. And the way we can prove this is just by substituting j into here. So 2j minus 2 is going to be greater than or equal to 2 times 5 over 4 minus 2. That's going to be equal to 10 over 4 minus 2. That's going to be a half. That's greater than or equal to 0. So this means that this quantity in here will also be a natural number. Okay, might be a little bit confusing because we're dealing with fractions, right? And you're like, okay, why are we dealing with fractions? We're supposed to be dealing with natural numbers. The reason we have fractions here is we're just bounding it, right? We know that j comes from the natural numbers, but we're saying the smallest j could be is 5 over 4. So really the smallest j could be is 2. J can't be 1 or 0. And we can prove that to ourselves very easily. If we put j equals 1 into here, we get 4 times 1 is 4, minus 3 is 1, so n equals 1. But that doesn't follow this n is greater than or equal to 2. So that value of 1 is not in the set A. Similarly, for j equals 0, we'll get n equals negative 3. That doesn't hold by that, so we can't include that either. But when we get j equals 2, we have 4 times 2 is 8, minus 3 is 5, which is greater than or equal to 2, so we keep that in the set. And as j gets larger and larger, those values will still remain greater than or equal to 2. So yeah, this sort of just implies that j has to be greater than or equal to 2. It's just fractional here because of how the equation worked out. And then similarly here, 2j minus 2, we're trying to show that that is in the natural numbers. And so we can provide a lower bound by taking the smallest value for j and show that that indeed makes it greater than or equal to 0. If you wanted here, we could put 2 times 2 minus 2 coming from this bound right here, and that would give us 4 minus 2, which is equal to 2, which is greater than or equal to 0. So everything would follow nicely. But yeah, we've basically shown that it's a subset. More formally, we can write let m equal 2j minus 2, then x is equal to 4j minus 3, which is equal to 2m plus 1, and m is greater than or equal to 0. So that's shown the first part here, that a is greater than or equal to b. Now we just need to show that they're not equal to each other. And the way to do that is, as we did previously, find an element in one set that's not within the other. So let's think about what elements are within A. So if you recall, when I said j can't be 0 or 1, we just didn't include those elements in the set. But when j equals 2, we get n equals 3. So that's when j equals 2, we get n equals 5. So that's included within our set. Let's do another one. J equals 3. We get 4 times 3 is 12, minus 3 is 9. And one more, why not? J equals 4. 4 times 4 is 16, minus 3 is 13, and so on. Let's start enumerating some values for B, and hopefully we'll find one that's, not included. So B, k comes from the natural numbers, so when k is 0, we get 2 times 0 plus 1, so n equals 1, and n has to be greater than or equal to 0, so indeed 1 is included within B, and we can just stop there, and we can say A does not equal B because 1 is in B, but 1 is not within A. So now we've shown that they're not equal to each other, and A is a subset of B, So A must be a proper subset of B. Fantastic. Last problem, dealing with power sets. We're going to prove that the power set of A unioned with the power set of B is a subset of the power set of the union of A and B. Lots of terminology in there. I hope you remembered your terms. If not, I'll try to, recall them as we go along. But okay, we're trying to show that the left-hand side is a subset of the right-hand side. By now, we should be hopefully feeling a little bit comfortable that when we see the subset sign, the general procedure is we take an arbitrary element of the left-hand side and show that it's an element of the right-hand side. So, let X be an element of the power set of A, union the power set of B, and let it be arbitrary. So now there's a couple of cases to consider. Either X is an element of the power set of A, or it's an element of the power set of B. And the reason is that this union contains elements that are contained either in this or in this. So X could be in both of these, but it could also be in just one of these. So we have to split it up into cases. So case 1, X is an element of the power set of A. And then case 2 will be X is an element of the power set of B. And our goal is to show that it's also an element of the power set of A union B. Right? So I'll try to describe this with colors. If A equals the set of this red scribbly, and B equals the set of this green squiggly, with maybe a little bit of red in here, then A union B is equal to the set of the red squiggly and the green squiggly. Right? We're combining the two together. That's my best visual description I can give you here, with the time in mind. Anyways, so why am I doing this? If X is an element of the power set of A, then X is a subset of A, right? So X is subset of A. That's just by definition. So that means every element within X is also an element of A. But I think that tells us, that implies that X is also a subset of A union B. And the reason for that is because all elements in A are contained within A union B by definition. This red squiggly is contained within here, so each part of this red squiggly is also a part of A union B. So the set X is a subset of this. Therefore, if X is a subset of A union B, then X must be an element of the power set of A union B, because the power set of A union B is the set of all subsets, and X is a subset of A union B, so it has to be contained within there. Case 2 follows pretty similarly. So this tells us that X is a subset of B. So X subset of B. And that tells us that X is also a subset of A union B, using a very similar logic. If every element of X is included within the set B, then it must also be included in A union B. All elements of X must be included within A union B, because no elements of B are deleted when we form A union B. That's the main thing to think about here. When we form A union B, we're only adding more elements to B. We're not taking any away. Similarly, we're only adding more elements to A. We're not taking any away. So that's why this property holds. And then we can follow that X must be a subset of the power set of A union B. And that completes the proof. We've taken both cases and we've shown that it's an element of the right-hand side. The biggest thing I want you to do is that if this part here was a little bit confusing, take a moment to rewind, re-listen to what I say, and really think about why that's true. If it helps, write out some examples, assign values to A and B, and prove to yourself why that's the case. Because these implications are very critical in set proofs, where we take this one statement and we expand it to something else here, where we start with X is a subset of B, but that also means it's a subset of A union B. So please take the time to show, like, prove to yourself why that's true if my explanation didn't make too much sense. And think about, does this imply that X is a subset of A intersect B or A set minus B? Expand that questioning to other set operations. But yes, this is the key line right there. Similarly, right here. So please prove to yourself why that's true. And that's the last example of the video. Hopefully, this was helpful. A nice little introduction to sets and set operations, and our first video in the discrete math series. Hopefully, you enjoyed. I'm excited to make more videos. Hopefully, you're excited to learn more. Until next time, take care.